this ball is going to sit there forever until something comes along and changes that. And while this might sound like the most stupid, obvious statement that I have ever made, it is still 100% true. And it teaches us a little bit about physics. This week, we're going to be talking about Isaac Newton and his 3 laws of motion, because understanding the 3 laws of Newtonian motion helps us predict what's going to happen in the future. And we can pair that with some of the things that we've already learned to get a good picture as to not just how things are moving, but why things move the way that they do. So, this week we're dealing with the 3 laws of motion, and we're starting with law number 1, which this ball is currently following. Newton's first law of motion famously states that an object in motion will stay in motion and an object at rest will stay at rest unless acted upon by an outside force. And while this seems like a ridiculously simple statement, I want you to think about the fact that you've never actually seen this play out in real life. So in the 1600s, when Isaac Newton is doing his physics thing, he's trying to escape the Black Death, which is killing people in cities. And so he runs out to the countryside and begins pondering the universe, because that's what you do when you don't have internet and cell phones. You ponder the universe. And as he pondered the universe, he thought about what makes things move the way that they do. And so I want you to think about this for a moment. If I take this ball and I push this ball, it's going to roll a little bit, but it will eventually stop. And that is the understanding that the ancient world had, or not so ancient, it was only a couple hundred years ago, as far as how things work. They were like, anything that is in motion will eventually stop. But that's not really what's happening. In fact, if I was to take all of the friction off of this table and roll the ball again, it would keep rolling forever until it hits something that would apply an outside force to it. And so Newton's concept of this outside force is really pretty revolutionary, because it told people that friction is the thing that we need to consider, and that an object in motion will actually stay in motion unless something acts to stop it. And on the flip side, an object at rest will stay at rest unless something decides to come along and move it. Now, that's the most common understanding for Newton's first law of motion. The other thing that you really need to understand about Newton's first law of motion is that it describes something called inertia. Inertia is an object's resistance to a change in how it's moving. So this 2 kilogram weight here has a certain amount of inertia, and if I push it, it really doesn't move very much. It resists a change in its state. If I take this tennis ball, which weighs noticeably less than 2 kilograms, and apply the same push to it, it rolls further than the weight did. And so the difference between these two things, while you might be quick to say that the difference is their mass, that's only partially true. The real difference is their inertia. Now, lucky for us, mass and inertia go hand in hand. There are 2 different sides of the same coin. An object with a large amount of mass also has a large amount of inertia, and which, once again, is its ability to resist a change in motion. Now, this works in 2 ways. It acts both getting something started. It also talks about slowing something down, which is still a change in motion. If I take this 2 kilogram weight and throw it at something, it's going to have a much greater resistance to slowing down than the tennis ball will. And part of that resistance is its ability to do damage. That's why heavy things are typically used as projectiles when you're looking to hurt something. So it's all about inertia, and inertia and mass are related concepts. So that's Newton's first law of motion, and we get to apply Newton's first law of motion to Newton's second law of motion, which talks about what a force actually is. Newton's second law of motion is typically written as F is equal to ma, or the force on an object is equal to its mass times its acceleration. But the easier way to understand Newton's second law is that the force required to move an object or to accelerate an object is proportional to its mass, which sounds a whole lot like the inertia example that I was giving earlier. If I want to accelerate an object with a very large amount of inertia, I have to apply a very large force to it. So, while inertia describes an object's resistance to a change in motion, Newton's second law of motion gives us the keys for how to still cause those objects to move. We simply need larger forces. And so if I have an object that has a lot of mass, it has a very great amount of inertia, I have to either use a very, very large force to get it to accelerate quickly, or if I use a smaller force, I would understand it will accelerate at a much slower rate. Its speed is going to be changed by less. And you can see this when it comes to doing things like pushing cars or moving furniture. They're very large objects. It requires a large amount of force to get them to move anywhere. Now, Newton's second law seems really simple, but the equation that we get from it is one of the most important equations in physics. F equals ma is something that we're going to apply to a wide variety of situations because a force is still a force. It doesn't matter if it's a physical force or gravitational, magnetic, electrical, all of those things still function in the exact same way when it comes to moving an object from one place to another. So while the concept is simple, the equation is really important. And so I want you to keep that in mind. Now, Newton's third law of motion is usually the most quoted and also the least understood. So let's go ahead and take a look at the kind of the cherry on the top of this thing, Newton's third law. Newton's third law of motion states that for every action, there is an equal and opposite reaction. Or to give you the more technical version, for every applied force, there is a responsive force that is equal in magnitude and opposite in direction. And so to really understand what this means, you have to understand what's going on in a situation. So I'm going to go ahead and bounce this tennis ball, which is going to cause a really weird sound on the audio. And if I do that, we can see Newton's third law in action. So as the tennis ball comes down, it is going to go ahead and strike the table. And when it does that, it applies a force into the table, attempting to make the table move. Now, the table is fairly heavy, and the tennis ball is definitely not. But what happens is that as the tennis ball applies a force downwards into the table is going to respond by applying a force that is equal in magnitude. It has the same number, but opposite in direction onto the tennis ball. So the tennis ball hits the table also hits the tennis ball with an equal amount of force. The table is large. The tennis ball is not. Since we know that the forces are equal according to Newton's third law, we should be able to predict, using Newton's second law, that the tennis ball will see a sudden, fairly dramatic increase in its acceleration. The table, not so much. Does the table technically move? Yes, just a little bit. You will notice some acceleration, but you'll notice a much larger amount of acceleration on the tennis ball because its mass is a lot less, meaning it has less inertia or less resistance to its change in motion. And what I'm trying to get at when I kind of expand on these ideas is that all three of Newton's laws of motion work together to describe a situation. So I can have an object that has inertia, a tennis ball. I can apply that inertia down, or I can break that inertia. In this case, gravity is going to break that inertia. It's going to apply a force into the table, and then the table responds by applying an equal and opposite force back into the tennis ball, causing it to accelerate in a way that we can predict with Newton's second law. And if you lost me on that, that's okay. It's a lot to take in all at once. But over the next couple of weeks, we're going to be taking a look at different types of forces and how they all work with Newton's three laws of motion. So, get ready. Forces is probably the largest unit that we deal with in AP Physics, and it's the one that you'll need the most understanding of. But by the end of this thing, you will have a much better understanding as to how the universe works. So, let's get at it.